Here we're going to look at some important Taylor polynomials, and they might look intimidating at first, but honestly, knowing these is going to save us time because otherwise we would have to build these from scratch, and we're actually going to use these to help us create other Taylor polynomials, and it'll be a bit quicker. So we do have to try to remember what these are. So for e to the x, the Taylor polynomial centered at 0, and these are all centered at 0, looks like, so here what this says is the nth degree Taylor polynomial is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on, with the general term being x to the n over n factorial. So here how I try to remember this is that the exponential function is always positive. It's always above the x-axis. So all of these terms here are positive, and every degree is covered. So x to the first, x squared, x cubed, all the way up to x to the n. As opposed to, we'll take a look now at the Taylor polynomial for sine and cosine. So for sine, here we have the 2n plus first degree Taylor polynomial. And for cosine, we have the 2n degree polynomial. So what's even going on there? So the idea here is that for the sine function, when we see 2n plus 1, we should be thinking of odd numbers. This is how you find the odd numbers, 2n plus 1. And then 2n is how you find even numbers. So here what's going on is if we look at the expansion for sine, we have x to the first power as our first term, minus x cubed over 3 factorial plus x to the fifth over 5 factorial. These are all odd exponents here. So the general term includes an alternating piece, negative 1 to the n, because these terms alternate in sign. And then we have x to the 2n plus 1, that way of generically expressing an odd number, over that same odd number, 2n plus 1 factorial. And the cosine function, well, that starts at 1, and the next term, minus x squared over 2 factorial plus x to the fourth over 4 factorial, those are even numbers. So the general term is again alternating, negative 1 to the n, x to the 2n, even numbers, over 2n factorial. So how do we remember which one's which? We go back to our knowledge of sine and cosine, and we remember that sine is an odd function and cosine is an even function when we think back to precalculus and trig and our symmetry. So that's one way to remember that sine is odd and then cosine is the even values. Another thing that might help is they both alternate because if we think about their graphs, so the graph of the sine function starts at the origin and then oscillates from there, and the cosine function starts at 1 and then oscillates from there. So that oscillating part is why we have the sign switching back and forth. Again, cosine starts at 1, so there's our 1. So hopefully those are ways to help us remember the Taylor polynomials for sine and cosine. Arctangent is next here. And so this one centered at 0, the nth degree polynomial looks like x to the first minus x cubed over 3 plus x to the fifth over 5. So the general term, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. So here, it basically looks like the sine expansion, except the denominators are not factorials. So that's kind of the connection that I try to make here to help me remember what's going on with that one. And in fact, this subscript here could actually be 2n plus 1 as well. So I'm go ahead and put that because we're only ever going to get odd powers out of this as well. And then natural log of 1 plus x centered at a equals 0. So this one, the nth degree polynomial is x minus x squared over 2 plus x cubed over 3 minus, and the general term is negative 1 to the n, so these terms are alternating, x to the n plus 1 over n plus 1. This one's an interesting one, not quite as common as the previous ones, but still worth knowing. And this last one is special. We're going to talk about this in detail a little bit more, but the Taylor polynomial for 1 over 1 minus x centered at 0 is 1 plus x squared all the way up to x to the n. So we'll take a look at that one a little bit more. So something I want to mention here, all of these start with n equals 0. So starting with the 0-degree polynomial. And these are also Maclaurin polynomials since their center is at 0. So Maclaurin polynomials are just a special case of Taylor polynomials with a center of 0. Let's do an example here. Let's find the Maclaurin polynomial of degree 8 for f of x equals cosine of x squared. If we had to use the definition of a Taylor polynomial, we would end up having to take the derivative of this function quite a few times. And that is going to be kind of ugly. So the first derivative of cosine of x squared is going to require a chain rule. And then it's after that, the next derivative will require a product rule and a chain rule. It's going to get ugly quick. And that's not what we're supposed to do here. What we are supposed to do is have the Maclaurin polynomial for cosine in our back pocket. We should have that memorized. So we're going to start by remembering that cosine x is approximately its Taylor polynomial, which starts with 1 because cosine starts at 1. And then it's the even exponents here. So 1 and the terms alternate. So minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So here, I'll actually go up one more, x to the 8th over 8 factorial. So this is a Maclaurin polynomial of degree 8 for just cosine x. Well, I want a Maclaurin polynomial for cosine of x squared. That's degree 8. So what I get to do is simply replace x with x squared. And so that I'm going to replace each x over here with x squared until I reach a degree 8 polynomial. So I have cosine of x squared now. So this is going to be approximately 1. I can't plug anything into 1. There's no x's there. And then I'm going to have minus. So instead of x being squared, we're going to have x squared squared over 2 factorial. Plus, instead of x to the 4th, I'm going to have x squared to the 4th over 4 factorial. And I actually get to stop already because here we are going to multiply the exponents together. And what we're going to end up with is 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial. And so here, if we want to, we can go ahead and simplify the factorials. So we have 1 minus x to the 4th over 2 plus x to the 8th over 4 factorial is 24. 4 times 3 times 2 times 1. So that's it. That was way easier than using the definition of building a Taylor polynomial and taking all of those derivatives. This is it. So it is an approximation. A Taylor polynomial or Maclaurin polynomial is an approximation, and we were told to stop at a degree 8. Now here, I do want you to notice I did use equal sign. So cosine x squared is approximately this function, but this line is equal to the previous line, and this line is equal to the previous line. But overall, this answer is approximately cosine of x squared. Here we want to find the Maclaurin polynomial of degree 5 for f of x equals x times e to the negative x. So again, we're not intended to use the formal definition where we take a bunch of derivatives. We're supposed to recognize that within this product here, I have e to the x involved. So we're going to start with what we know of a Maclaurin polynomial for e to the x is. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. So I'm stopping there because we eventually want a degree 5 Maclaurin polynomial, but not just for e to the x, for x times e to the negative x. So we're going to do this in phases. First, we're going to replace the x here with a negative x. So what that's going to leave me with is e to the negative x, where negative x is going to replace each x up here. So 1 minus x plus negative x squared over 2 factorial plus negative x quantity cubed over 3 factorial, negative x all raised to the 4th, negative x all raised to the 5th. So anytime we have a negative raised to an even power, that's just going to eat the negative. But if we have a negative raised to an odd power, the negative is going to stick around. So that's going to leave us with these alternating terms. So 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial and minus the x to the 5th over 5 factorial. And now the final step is we want to go ahead and multiply through by an x. So we currently only have e to the negative x represented with a Maclaurin polynomial. So we're going to multiply each term here by an x. So that's going to leave us with x times 1, x times x times this x squared over 2 factorial, an extra x times x cubed over 3 factorial, and we're going to stop at x times x to the 4th over 4 factorial because that product there is going to leave me with a degree 5. So let's just clean this up for our final answer. So we're going to have x minus x squared plus x cubed over 2 minus x to the 4th over 6, which is 3 factorial, plus that degree 5 term, x to the 5th, over 24. At the beginning, I mentioned 1 over 1 minus x was special, and we were going to talk about it. So what is special about f of x equals 1 over 1 minus x? Well, 1 over 1 minus x has the form a over 1 minus r, which is the sum of a convergent geometric series. Notice that a is equal to 1, which is the first term, and r is equal to x, which is the common ratio. So assuming that the absolute value of x is less than 1, because we know that the common ratio, r, in absolute value bars has to be less than 1, then we have 1 over 1 minus x is the sum of an infinite geometric series. So 1 over 1 minus x in expanded form can be written as 1 plus x squared plus x cubed, because what's happening is 1 is the first term, so the number on top is the first term, and then to get from term to term, we multiply by the common ratio. Well, we said r, the common ratio, is x. To get from one number to the next here, we are multiplying by a copy of r each time. So in summation notation, we have that 1 over 1 minus x is equal to the sum of n equals 0 to infinity of x to the n. But we want a Maclaurin polynomial, and polynomials end. They have an nth degree. So what we have to do is just cut off this series at some point to get an nth degree polynomial. So 1 over 1 minus x is approximately 1 plus x squared all the way up to x to the n. But that only works for x values between -1 and 1, because this is the same as the absolute value of x is less than 1. Now, note, you can also obtain this result using long division. So we can divide 1 divided by 1 minus x using long division, and we would also get this sum here. So there's different ways to obtain it, but this is a really nice way, and we want to recognize this way for some examples we are about to do. Here we'll just briefly look at some Maclaurin polynomials for 1 over 1 minus x of degree n. So 1 over 1 minus x is a reciprocal function here, so it's these pieces, and this line is the degree 1, a linear degree 1 Taylor polynomial or Maclaurin polynomial. Degree 2 is this parabola here. So it's a little bit better of an approximation. This line is pretty terrible. It's only close right near 0. This parabola stays close to 1 over 1 minus x for longer. This cubic function here stays close to this curve a little bit longer. Degree 4 polynomial here stays even closer to 1 over 1 minus x for longer. Then I have n equals 5, a degree 5, a degree 6 polynomial. But none of them are very good approximations over here to the left of -1, and none of them attempt to approximate this piece over here that would exist on the graph of 1 over 1 minus x. So notice that like our previous Taylor polynomials that we studied in the last section, they match the function perfectly at the center, x equals a. So at 0, the 6th-degree Taylor polynomial matches 1 over 1 minus x, but they lose accuracy as we move away from the center. So as I start to get further away from 0, I can see this gap between the polynomial and the actual curve. And they gain accuracy as we add more terms to the polynomial. So the degree 1 polynomial was just a line, and that was a pretty terrible approximation, but this degree 6 one is better. It stayed closer to the function for longer. However, we do not appear to be able to extend the interval indefinitely, no matter what degree polynomial we go to. So it looks like our polynomial is only going to work between that -1 and 1 set of values, right? And that's because 1 over 1 minus x was approximately this geometric series, and it only works to have a convergent geometric series when the absolute value of the common ratio is less than 1, or where x values are between -1 and 1. So now, why build a Taylor polynomial for f of x equals 1 over 1 minus x? This is a really easy function to work with. If I want f of 4, I can just plug in a 4 right here and easily evaluate this. Well, again, 1 over 1 minus x has the form a over 1 minus r, which is the sum of a convergent geometric series. So what we want to do is extend this idea. We were able to easily build a Taylor polynomial for 1 over 1 minus x. Turns out, given a function of the form f of x equals a over 1 minus some r of x, we can build the Taylor polynomial. So a over 1 minus r of x is approximately the first term, a, plus a times r of x, so that common ratio r of x, we are multiplying by that to get to the next term, and then we multiply by another copy of r of x, which would be r of x squared, and so on. So we can easily build a Taylor polynomial for something of this form, and that is provided that the absolute value of the common ratio is less than 1. That's when this expansion will approximate this function. Let's do it. Let's do an example. So find the Maclaurin polynomial of degree 6 for f of x equals 3 over 1 minus 2x. So here we are trying to make sure that we have that form a over 1 minus r. And we basically do. So here the a value is 3. And then we have 1 minus r. So the r value is 2x. So that means that 3 over 1 minus 2x is approximately the first term, 3, plus now we're going to multiply 3 times a copy of r. So we're going to have 3 times 1 copy of 2x. And then the next term will be 3 times 2x squared. So we multiply by another copy all the way until we get to a degree 6. Right now, x is only being squared. So we're going to have plus 3 times 2x cubed plus 3 times 2x to the 4th plus 3 times 2x to the 5th, and then plus 3 times 2x to the 6th. And then it really is just a matter of multiplying the coefficients. So this is 3 plus 6x plus here, 2 squared is 4 times 3 is 12. So 12x squared plus 2 cubed is 8. 8 times 3 is 24. So 24x cubed plus 2 to the 4th is 16. 16 times 3 is 48. X to the 4th. 2 to the 5th is 32 times 3, so 96 x to the 5th. And 2 to the 6th is 64. 64 times 3 is 192 x to the 6th. So this is the approximation, the polynomial of degree 6 for 3 over 1 minus 2x. But this only works for the set of values where the absolute value of the common ratio r is less than 1. So we can pull out the 2 and then divide by that. So absolute value of x is less than 1/2, or in inequality notation, when x values are between -1/2 and 1/2. So it's this polynomial when the x values are between 1/2 and -1/2. Now we want to find the Maclaurin polynomial of degree 4 for h of x equals 4 over 2 plus x squared. Now this sort of has the form we're looking for, but not quite. We wanted a over 1 minus r. So the problem here is this 2. So what we're going to have to do to start is we're going to have to make this a 1 through division. So we're going to multiply the top and bottom by a half, or divide the top and bottom by 2, however you want to think about it. So if we multiply the top and bottom by half, or divide the top and bottom by 2, what's going to happen is 4 times a half is 2, and then this 1/2 will distribute over here. So we're going to have 1 plus 1/2 x squared. Now it still doesn't quite have the form a over 1 minus r. I'm going to rewrite it as 2 over 1 minus -1/2 x squared. So now our a value is 2, and our r value is -1/2 x squared. Or another way we could write it is -x squared over 2. All right, so we have 4 over 2 plus x squared is approximately a, our starting value is 2. Right, that's what we got over here, 2. And then we're going to multiply 2 by the r value, -x squared over 2. And then we're going to do it again, 2 times -x squared over 2 squared. And I'm actually going to stop because I wanted a degree 4 polynomial. And if I notice here, x squared squared will give me an x to the 4th. So let's just clean this up a little bit. We have 2 here. It's going to stay negative. So we're going to have -x squared. So the 2 divided by 2 cancels. And then here, we're going to have, let's see, 2. So plus 2, and then we're going to have x to the 4th over 4. So the negative gets squared out. X squared squared is x to the 4th. 2 squared is 4. And then let's simplify. There's a 2 on the bottom there. So 2 minus x squared plus x to the 4th over 2. But this only works when the absolute value of the common ratio, -x squared over 2, is less than 1. Okay, so the absolute value is going to ignore the negative. So absolute value of x squared, and I'm going to pull the 1/2 out, is less than 1. Multiply by 2, absolute value of x squared is less than 2. Well, absolute value and x squared is kind of redundant because absolute value makes things positive, but x squared is already going to be positive. So what we really have here is just solving x squared is less than 2. When we have a quadratic inequality, we typically want to do this with a graph or a number line. So how I'm going to interpret this problem is I'm going to think about it as x squared minus 2 is less than 0. I'm going to subtract that 2 to the other side. And so I'm going to do just like a quick sketch of x squared minus 2. That's a parabola shifted down 2 units. So here's a quick sketch. The y-intercept would be down at -2, and the x-intercepts are going to be plus or minus radical 2. So when we solve this inequality, we can think about when is this less than 0 or below the x-axis. And so that's going to be all the set of values between negative radical 2 and positive radical 2. So for these x values, that's when this function is approximately this Maclaurin polynomial.